Good morning, everyone. Today, my partner and Edwin and I are going to present our final IoT case study project, the Smart Classroom Ventilation Controller. Modern university classrooms are highly sealed, air-conditioned space designed for thermal comfort. However, this creates an invisible threat. The rapid accumulation of carbon dioxide generated by high-density student occupancy. Current institutional HVAC solutions face an efficiency problem because of either fixed mechanical timing or continuous operation. Our goal was to build an airflow system according to real air conditions. To solve this problem, our proposed architecture will apply a network-centric approach strictly. Unlike using localized edge microcontrollers that have separate firmware and maintenance individually, we use Cisco IoT registration server. All hardware components in the system serve as individual nodes of the network using regular IP addresses over the centralized workgroup switch in the classroom. The control loop functions as an automated threshold response system. In the central server initiates an automatic dual mechanical response to vent out the CO2 through the activation of both the smart fan and the smart window. For environmental sensing, we utilize a network-enabled CO2 detector. The physical actuators comprise a smart ventilation fan and a mechanical smart window. The entire local topography is collected through a Cisco Catalyst access switch, which handles hardware packet distribution. Let's walk through the system data flow. At the edge layer, the CO2 detector constantly samples the classroom air. This state is captured in TCP/IP packets and passed upstream through the classroom switch to the IoT server. Inside the server, the data hits a real-time conditions engine. If the threshold is breached, the engine sends back the control packets downstream through the switch to modify the state of our actuators, forcing the fan to spin up and the window to open. If the air quality returns to a safe zone, the server immediately sends a standby macro to turn the fan off and seal the window to retain the indoor air conditioning. The monitoring PC sends HTTP requests to get the real-time UI dashboard from the server. From the network scaling point of view, we follow the classic three-tier hierarchical network design model. Each classroom functions as an independent block at the access layer. The switches from there are connected to distribution switch within the buildings that provide clear communication. All data aggregates at the campus core data center managed by a single central server dashboard. To ensure corporate-grade security, our network complete IoT VLAN segmentation to block unauthorized public Wi-Fi access. And that is all from my part. I will pass to the next presenter, Edwin.
All right, thank you, Sen. So our primary milestone is the integration of occupancy gate logic with PIR sensor. By adding a passive infrared sensor to the access network, our server's logic engine will evolve into a strict dual gating condition. The server will ensure the windows and fans operate only if there is a CO2 breach and a human occupancy is confirmed. This ensures windows remain securely closed during the high CO2 weekends or overnight periods. In phase 2, we will integrate the machine learning predictive analytics right into the server, using room bookings secure to pre-ventilate the lecture halls with high occupancy 10 minutes before the start of classes. Finally, phase 3 will include integration of our system into the fire and life safety grid of the campus. In case of emergency, safety override will turn all fans off and open all windows for ingress routes. Next. So in conclusion, this case study successfully simulates a scalable environmental automation system within the Cisco packet tracer. Our key lesson learned from the entire engineering effort is that separating the automation logic from local microcontroller chipsets and putting it on the enterprise server will dramatically reduce the deployment cost in the maintenance. So next, I'm presenting the virtual networking scalability and the security simulation phase of our smart classroom ventilation controller project. Before deploying the physical hardware prototypes like the ESP32 and the Sensirion NDIR sensor in a live enterprise campus environment, it is critical to model the network topology, test multi-subnet addressing, and validate the defensive routing rules. To achieve this, we utilize the Cisco packet tracer. Our primary goal, shift from a simple single-room model into an enterprise-grade multi-subnet campus architecture. This ensures the system can dynamically scale across the multiple buildings while actively mitigating the network security threats. Now I'm showing you our main packet tracer workspace. Let's look at the underlying topology designed to handle the enterprise scalability. In a large campus environment like Multimedia University, placing hundreds of smart environment nodes on a single flat network creates the massive broadcast storm and the network lag. To address this, we engineer a route multi-subnet framework using a Cisco 2911 core router as our central gateway. So we expand the network into two discrete. Simulate the classroom zone running a sequential subnet. Classroom 1 subnet on 1.1.1.0/24 representing our initial block A layout. For classroom 2, subnet on 1.1.2.0/24 representing a ejection block, considering it's on the independent the smart sensor and the ventilation fans. So every endpoint connects to a standard layer 2 switch using physical copper straight-through cabling. To align with hardwire industrial reliability, we manually modified the I/O configuration blocks of the smart device, swapping their default wireless model out for physical fast internet adapter. Now I will show you the connection lines for the gigabit Ethernet 0 and the 01. So the toy tips for up display the IP gateway 1.1.1.254 and the 1.1.2.254. So because of IoT actuator control the physical building mechanically like height, voltage, exhaust fans, motors, and configure the network invite malicious the tampering. So we implement two strict security mitigation strategies directly inside the CLI. First, we configure the network segmentation using the VLANs. On our main switch, we isolate all hardware interface connect to our environment system into a secure VLAN 10 named Secure IoT Network. So this establishes a logical boundaries line ensuring that if a student plug a root laptop into an unassigned campus wall port, they remain locked out of the IoT data plane entirely. Second, we implement a firewall strategy using a standard access control list, which is SCL, on the core router. our rule states that only traffic originating from the authorized MMPC at IP 1.1.1.2 is permitted to route inbound management command to the server. So while traffic from the unauthorized subnet is dropped at the gateway. Now I click on my main switch. So now we type the show VLAN brief. As you can see, our VLAN 10 and the name Secure IoT Network active on the screen. So with the route path secure, all endpoints route telemetry across the gateways to register back to our central registration hub at 1.1.1.1. Our automatic gating logic monitors the environment in real time. When the vehicle engines are turned on to simulate a heavy generation of bio and fluid, the carbon dioxide sensor telemetry spikes. The instant gas concentration peaks as the 0.6 and the server executes an emergency state. It roll up the garage door, slide open the windows, and trigger the exhaust fans to spin at step 2 for maximum visualization speed. So once the active extraction flows out the contaminants and the gas level drop below our safe clearance threshold of 0.5%, the environment automatically winds down to a low power standby mode to protect the university and then utility budget. So as you can see, so as I mentioned just now, if the carbon dioxide level is clearance zeros of under 0.5%, so the window and the door will close. And if we over the 0.6%, the exhaust fans window and the door will open. So to verify that our scalability and security configuration are running flawlessly, we can execute a network connectivity test. So to verify that our scalability and security configuration are running flawlessly, we can execute a network connectivity test. When we ping classroom to smart sensor from our management PC, the ICMP package cross the router interface seamlessly, providing our multi-room scaling design works perfectly. However, if an unauthorized device attempts to send packets to the secure backend server, the router access controllers drop the stream suddenly, proving our security mitigation is completely active. Ultimately, this packet tracer simulation successfully demonstrates that our smart classroom virtualization controller can scale seamlessly across an entire university block while maintaining enterprise-grade network security boundaries. So thank you, and my partners, Shen, and I am now happy to take to our network configuration. So as you can see, the pin from MMPC to the router is successful. That's all for us. Thank you.